Today's lesson is going to focus on a family called carboxylic acids. Carboxylic acids contain a functional group that is called a carboxyl. And like the name implies, the carboxyl is referring to a carbonyl group and a hydroxyl group that are linked together. So the carboxyl group, we say, is sort of like a half-half mixture of the carbonyl and the hydroxyl. So you'll see them there all joined up. But together, collectively, this is the functional group for a carboxylic acid. These carboxyl groups are always located at the beginning of a carbon chain. So you'll see them at, one end or the other, and whichever end you see the carboxyl group, that's where you begin numbering your carbon chain. Because they are called acids, right? They're called carboxylic acids. They are not actually strong acids. You might recall from our previous lessons on acids that you can have weak acids and you can have strong acids. Strong acids break down or dissociate 100% in water. Weak acids break down less than 50%. Carboxylic acids are weak acids. So they only break down less than 50% when placed in water. And as a result, humans can consume a lot of weak acids. And we actually do consume a lot of carboxylic acids in small amounts. We still can't consume large amounts of it because, again, it still can cause harm. Okay, so if you drink a jug of vinegar, you're not going to feel good. But vinegar is a carboxylic acid. It's called ethanoic acid. Citric acid that we find in citrus fruits, that's the type of carboxylic acid as well. There's many, many different kinds. Carboxylic acids are unique because they have very high intermolecular forces. So these guys are always the winners when you talk about boiling points and attractions between molecules or how attracted they are to water. And the reason is, if we just split this apart, you're going to see here we have two carboxylic acid molecules that are attracting each other. And the reason that they're attracting each other is because we have a dipole running through the carbonyl. And then we also have another dipole running through the hydroxyl. And that hydroxyl, because it is polar, it creates a positive charge on the hydrogen. So you end up with hydrogen bonding here. So let's clean this up and then show you where this hydrogen bonding takes place and then why it creates an even stronger attraction. So remember that we're going to have these, my pen. So we're going to have these attractions between neighboring dipoles. So right here, we'll show that happening, negative and positive. And then again, right here, we have a negative end and a positive end. And then there's a little dipole on that hydrogen as well. So you've got all kinds of attractions here, like extra reinforcement between molecules. Same thing happening here. This end is negative. This end is positive. The hydrogen is also positive. And so on these neighboring molecules right here, you're going to get really strong electrostatic attraction. I've made a bit of a mess of that diagram. I think you get the idea. So in addition to dipole attraction, carboxylic acids have two dipoles, right? Because they have one through the carbonyl. They also have one through the hydroxyl. And they also have this hydrogen bonding phenomenon because the hydrogen in the OH is slightly positive. So when two carboxylic acids come together, there is a lot of attraction and it takes a lot of energy to separate these molecules from each other. When we name carboxylic acids, we are looking for the longest chain that includes the carboxyl group. So I'll just do a diagram here. Here's an example of what we would look for a carboxyl group. You have to remember that right here, there is a carbon. So this would be carbon 1, 2, 3, and 4. And if I did a molecule like this that did not have any branches or any pi bonds, It's a 4-carbon parent, so a butane. We lose the E and we replace it with oic acid. So it's 2 words, butanoic acid. Let's do another one here. So I'm going to put my carboxyl, on that end. And then maybe I'll throw a pi bond down. Let's do some branches right here. So again, don't forget that there's a carbon here. Sometimes students forget, and I see them numbering like the next carbon over. So 1, 2, 3, 4, 5, and 6. So I have methyls on 4, 5 dimethyl. And then I have a pi bond on carbon 3. So I have a 3-hexene and then oic acid because it is a carboxylic acid. And you don't need to say 1 oic acid because that's where you have to start numbering. And so those are examples of carboxylic acids. They can form cyclic molecules. We won't see them. So this is as tough as it gets with them.